In electronic circuit, some components require just a fraction of the input voltage in order to function properly. One of the ways to reduce this large voltage to smaller ones is by using the voltage divider circuit. In this video, you will be learning what a voltage divider circuit is, its governing equation, and since we are engineers, we will apply these equations in order to avoid trial and error. The voltage divider circuit consists of two major components. We will be varying the values of these components. We will call them conditions. There are three of them. We will simulate these three different conditions in Proteus to see their real-life behavior. Stay with me to the end of this video to learn all about that. The voltage divider involves applying a voltage source across a series of two resistors. It is drawn in a few different ways, but they should always essentially be the same circuit. In the first representation, you will have V in going down to a resistor called R1, then extending to another resistor called R2, then to the ground. Now at this junction, this is R2. Now at the junction here, you can tap out your V out, which is always a ratio of the input voltage. Now we'll be able to derive an equation later on to show you this relationship. Now, this is another representation of this circuit. You have something like this, then you have the R1 coming down to R2, then going back to your supply V in. It can be a battery, maybe a battery source. You can have a battery source this way, coming in as your V in here. Then this is R1, this is R2. At this junction, you can tap out your V out. This is another circuit of the voltage divider. Now, there's another representation you can have. This is V in coming in to a resistor, then going out. Then there's a junction here, coming down here. Now, here, this is your V out. Now, this is R2, R1. Now, these are three representations of the voltage divider circuit. However, they are being represented anywhere you see them, you can identify them like this. Now, there is a relationship between the V in and V out, and it is a function of a ratio of this and this. Now, this is the ratio. The ratio is normally your R2 all over R1 plus R2. This ratio is what is multiplied by your V in to get a value called V out. This is your voltage divider equation. These are the voltage divider circuit, and then this is the equation. Now, all the values that you can ever get from V out has a behavior with respect to the value of R1 and R2. There are a few generalizations that are good to keep in mind when using voltage dividers. And the first condition is, what if we have R1 if R1 is the same thing as R2? Now, if you have this the same thing as this, there's a behavior you will always have of V out with respect to V in. Let's check and explore this condition. If R1 equals to R2, let's represent it by something like R. Just call it R. Now, in this condition, what you will have is V out from here now, right? It's equals to V in multiplied by, now, we said our R1, which is R2 here. I want to put this equation here. Our R2 here is the same thing as R. So you just go ahead and put R all over R1 plus R2, which is R plus R. So what you're going to have is V in multiplied by R over R plus R is 2R. So what you're going to have is, you cancel this out, is V in all over 2. Now, what I'm having here is just this equals to this. So V out is the same thing as V in all over 2. So whenever you are expecting an output voltage, it is always half of the input voltage if R1 and R2 are the same. So whenever you have an input voltage, let's say 10 volt, and you want to have 5 volt, all you need to do is to set up a voltage divider circuit like this anywhere. Just get two values of resistors that are the same. What you're going to have is that the output voltage would be half of the input voltage. So if I give it 10 volt and I want 5 volt, you just have to set up this voltage divider circuit and make the values of resistors the same. What you will have is half of the input voltage. Now, this condition is what we're going to test right now in Proteus. I'm here at Proteus, new project. Let's call this project same resistor. So I'll go to pick devices. I'm searching for a resistor. I've found one here. This is okay. Now I will also need a generator, a DC generator. So I'm picking a DC voltage source here. Then I will need an instrument called a DC voltmeter. Okay, so I need another resistor. I need to rotate this. Then I'll connect this and this to this. Then we need a ground here. Click here, ground, and this is it to the ground. So this, I need this somewhere here. Okay, somewhere here. Okay, so let me bring them closer so that when I zoom in you can see that clearly. Okay, so what we have here, I'm going to supply a voltage source of, let me say 12 volt. So I expect that since these two resistors are equal, from our voltage divider principle here, when these two resistors are equal, the output here should be half of this volt here, which is 12 volt. This supply here, that is 12 volt, the output should be half of this 12 volt, which is 6 volt. So let's simulate and see. Voila, we are here. This is 6 volt, as you can see. Okay, so what I will do now is, let me change the value of these resistors. Let me say 55k, but they have to be the same. Same thing here, 55k. Okay, so let's simulate that. 12 volt here coming down to 6 volt. Let me change this input volt. Let me put 230 volt as DC. Half of 230 volt is 115 volts. So can you see that? This is how to simulate for two resistors that are equal in a voltage divider circuit. So now let's move on to analyze for another scenario. Right now we want to test for another condition where R2 is far greater than R1. But before that, let me make something very clear to you. I think something you should always remember. In a voltage divider circuit, there are two major resistors. One is the R1 and the other R2. Always remember that the R1 is the resistor connected to the V in. That's the voltage in. And then the R2 is the resistor connected to the ground. And also, you should remember that the voltage across R2 is what you get as V out. Alright, that being said, let's go back to check our condition in this very section of this tutorial. So we want to consider a situation where R2 is far greater than R1. So let me write it here. If R2 is far greater than R1 in terms of magnitude, to the point that R1 doesn't exist, let's push it to the maximum limit and see. So that means R1 becomes 0. So what happens? Let's substitute it in this equation and see what happens. So V out is equal to V in R2 divided by where R1 is 0, 0 plus R2 to give you V in. Then you have R2 divided by R2. Here we cancel. Then you have just this V in. So V out is equal to V in. So whenever R2 is far greater than R1 to the point where R1 is completely insignificant, what you will get is that the voltage out will be equal to the voltage in any voltage divider circuit where R2 is far greater than R1. So let's go back to Proteus now to verify this condition. Okay, so we're back to Proteus again. The same circuit. We're going to use this same circuit to test for our second condition. But first of all, did you notice that our labeling was not correct? Our labeling for the resistors, this is supposed to be R1 and this is R2. It doesn't matter. Your labeling can be anything, but in the structure of a voltage divider circuit, we all know that our R1 is the resistor that is close to the input voltage, and then R2 is the resistor that is connected to the ground. And this is where the output voltage is gotten from. It is a voltage across R2. So your labeling can be, you can label it, you can even call these resistors by your name. You can call it your name or anything. But just for clarity's sake, so let's change the labeling. You can just right click, you edit the label, call that R1. But we already have an R1, need to complain. Just ignore that. This is R1, you do the same thing. Edit R2. And then here we have the resistors are having the same values, but remember we want to make sure that R1 is far greater than R2. So this is 55 kilo ohms and this is also 55 kilo ohms. So let me just remove the K here. So I'll change the value. I want to do that in the ohms. That's resistance in ohms here. So I'll just remove the K. So 55K is far greater than 55, right? That's 55,000 ohms with respect to 55 ohms. This is far greater. We all know that. So what about the input voltage? How many volts do I want here? This is 12 volt. I can change that to any volt. Let me put 36 volt. Just any amount, just for any convenient voltage, you can put that. So I want to write the same. Let me change the label to the same 36 volt. So this is 36 volt. Now I'm going to simulate that. If this is true, if this our condition is true, that whenever R2 is far greater than R1, what would be the output voltage here? Yeah, I know you already know that. The output voltage we're expecting to be the same thing as the input voltage, which is 36 volt. Now let's do that. Yeah, this is 36 volt. Can you see that? This is 36 volt because this is greater than this. So you can mess around with it. You can change that. Let me do that again. Let me put another volt. Let me put 5 volts. 5 volt. I can change that here too. 5 volts, just so that you see it here as 5 volt. And change the value of your resistors. Let me say let me put 30k. Yeah, I can just put anything. 25, 22 ohms. Very, very insignificant to this. So let me simulate now. The same 5 volt that is here is the same 5 volts that is going out. So this is actually true. This condition is true for a voltage divider circuit, that when R2 is far, far greater than R1, the output voltage is same as the input voltage. And whenever you are increasing these, we're going to talk about what would be the behavior in the next condition. Here we're going to find out the behavior of this voltage divider circuit if R1 is the resistor that is far, far greater than R2. Unlike what we saw previously where we considered R2 far, far greater than R1, here we are checking for R1 far, far greater than R2. Now, if R1 is far, far greater than R2, to the point where R2 doesn't exist, or it's almost, or it is insignificant. So let's represent R2 with 0. So let's substitute the value where for R2 to be 0 in this voltage divider equation. So we have V out equals V in multiply by R2 now is 0 divided by R1 plus 0. So this will give you 0. So that means V out is equal to 0. So what this means is, for a voltage divider circuit like this, whenever R1 is far, far greater than R2, V out becomes 0. V out becomes 0. So the applications of this voltage divider circuit in real life is going to be very interesting to you. So we will do that in the next session. But before then, we're going to test for the viability of this scenario, this equation, and this circuit with the value of R1 far, far greater than R2. We're going to check that in Proteus to see if this is true. So let's go to Proteus now. Back to Proteus again to test for the condition where R1 is far, far greater than R2. Now let's change the value of the resistor here for R1 to be far, far greater, or let's leave it like that and then reduce this. And to reduce this, let me just remove the K here. So it means we have 55,000 ohms compared to 55 ohms. This is far, far greater. We all know that. So, and this, the supply voltage here is 5 volt. Can you see that? It's 5 volt. So what do we expect when we simulate that from what we've computed earlier on? Of course, you know what to expect. Let's try that now. Yeah, the output volt is 0 because this is far, far greater than this. R1 is far, far greater than R2. So let's change the values here again and see what the behavior would be like. Okay, here ohms, let me put 5k. I want to reduce this to 1 ohms. Still 0. This is far greater than this. This is almost approaching nothing. Then this would give you 0 as nothing here.